Yes, yes.
Okay. So, good morning, everyone, and very thanks for the nice introduction. Today, I wanted to talk about challenges of computational astrophysics, specifically with black holes. So, to zoom in, I'll be talking about numerical relativity as it is applied to systems made of purely black holes, the status of the field, and where we are going in there. So to start with, let's put the problem into some astrophysical context. We know that we are observing gravitational waves from binary mergers, compact binary mergers, quite regularly with the ground-based interferometers nowadays. Black hole binaries emit gravitational waves, and they are the primary sources of these signals for the current terrestrial detectors. So these orbiting systems of binary black holes, they continue to emit gravitational waves, and as they do, their orbits shrink and they come closer to each other until they reach a point where they are close enough that they coalesce or a common horizon or the distorted black hole is formed, as you can see on the figure at the right bottom, which then settles down into a Kerr black hole state at the end by radiating away its anisotropies and again in the form of gravitational waves. So that's sort of the kind of system that we are interested in studying in full nonlinear relativity. Now, gravitational wave observations with LIGO have been many. Nearly 100 had been seen in the first few observing runs of these instruments. In fact, this figure here shows a collection of all the compact objects that have been seen by the ground-based detectors so far. So the ones in blue are all LIGO Virgo observed black holes. The ones in purple are the black holes that had been observed before LIGO Virgo era, specifically through indirect emission of electromagnetic radiation and so on. And the objects at the bottom in yellow and orange are neutron stars that have been observed over the past few decades. So the thing to note from this is that above, so I've drawn a horizontal white line over here. All the black holes that lie above that white line are massive enough that it is really the last stages of their coalescence that is visible to the ground-based detectors, which means the very last stages of in spiral, this merger portion, as well as the settling down of into the final post-merger black hole. That is what comprises the major fraction of the signal that is visible to LIGO and Virgo detectors. Now, this fact is again illustrated here. So, for example, I've picked three specific binary black hole merger events. GW 150914, that was the very first event. Then GW 151012 and 151226. And they are sorted in order of decreasing total mass of the system. Now, the larger the total mass, the lower is the frequency, or the longer are the time scales associated with this system in GR. So the heaviest of these objects, they emitted at the lowest frequencies. So that would be the blue signal on the right. And the corresponding frequency domain signals and are shown in the figure on the left. So on the left, you can see in the same exact colors, the three different signals overlaid on top of the LIGO Virgo noise spectra, or the which illustrates the band of frequencies within which we are able to see gravitational waves from these systems. So the main point, as from the previous slide, is that the more massive binaries we see, the more strong field, truly dynamical, non-linear, general relativistic effects we actually measure, right? And that is good because that helps us understand gravity in its more and more extreme regimes. Okay. So what has been the role of numerical relativity in this science? So I've drawn a small flowchart here, and that depicts how from the level of observations to inference, what all are the stages that proceed, that information proceeds through. So to start with, at the top left, we have the actual compact binary source, the binary black hole source that is inspiraling and merging and emitting gravitational waves. These gravitational waves impinge onto this interferometric detector. The detector observes them. The data goes through a calibration stage. And that is where it is actually ready for some analysis. The first analysis stage comprises of a match filtering stage. And that stage uses a large collection of GR-based waveform templates, which are nothing but theoretical predictions of what these gravitational wave signals should look like based on our understanding of these binary black hole, binary neutron star systems, right? Beyond this stage is a second stage which checks for whatever triggers come out of the first stage. It checks whether those triggers are truly astrophysical in nature or not. And that's the signal consistency stage. And it also uses the same collection of waveforms from theoretical understanding of GR. After these two stages, typically we have a large collection of triggers coming out. Most of these triggers are chance triggers from pure noise events, and those form a background that is shown in red here. You can see the background has its own pattern as a function of the reweighted SNR corresponding to each trigger. And any real signal typically stands out far above this background. And that is how we know that we have detected a gravitational wave signal clearly. Once we have detected this, we take that specific chunk of data and we perform a detailed Bayesian parameter estimation on it to understand what was the nature of the original source that emitted this signal. So you'll see that in all these three stages, being able to model the waveforms is key. And that is where numerical relativity comes in. So numerical relativity is typically used to perform simulations of these black hole collisions, black hole neutron star and neutron star collisions. And these collisions are then used to inform waveform models, which are in turn used to generate the large collection of waveform templates that are used by this machinery of GW astronomy. Okay, so numerical relativity really plays a central role in this science at the moment, especially because we have heavy black holes as the most popular sources of gravitational waves at the moment, right? In fact, numerical simulations are indeed necessary for binary black hole science. Um, That's because for the last several orbits before merger, for the merger itself, as well as the physics beyond merger, much of it can only be computed using fully numerical, fully nonlinear solutions of Einstein's equations. And this is the regime where analytical methods such as post-Newtonian theory breaks down. In fact, without using numerical simulations, many of our iconic GW events, like the very first one, 1509-14, and some others, would have been detected with much lower significance, sufficiently low that we may not even be able to claim them as the first detection, for example. And if 1509-14 source had been just quarter further away than it was, it would not have been seen in Livingston at all, and therefore it would not have had any detection for that event. And even if we see all of these sources, all of these signals, without this high precision information from numerical relativity, we'll not be able to understand the qualities of the source very well. In fact, for example, this figure on the right bottom illustrates that pretty nicely. So if you want to measure the mass and spin of the post-merger black hole from these coalescences, uh, with or without the results of these numerical simulations, what you get is the solid dashed curve versus the solid curve versus the two dashed curves here. And you can see really this information about the late stage dynamics is key to high precision measurements of these parameters. Okay. And obviously, as a corollary of this is that this allows us to test GR, etc., in its most extreme and dynamical regime. Okay. So how do we simulate So let in the next part of the talk, I'll talk about how we simulate black hole coalescences. So to start with, let me show a visualization to talk about exactly what kind of simulations is it that I am talking about here. So I hope you can see the YouTube video that I've just started playing here. Yeah. Okay. So what is being shown here is, oops. So what is being shown here is GW 150914's equivalent numerical relativity simulation. The two black holes are shown as the two horizons over here in the center. The color near the horizons, this is the spatial curvature, the 3dg scalar here. And far away from the source, the color is the outgoing gravitational wave. Okay. So yeah. And note that the two black holes here are spinning and their spins are misaligned with each other. So the cross terms between the two spins will generate a top, which will rotate the plane of the orbit over time. And so you will see that as the orientation of this orbital plane changes during the course of this movie, right? Okay. Okay. And the arrows here also show the rate of flow of time. The size of the arrow shows the rate of flow of time, and the direction shows the direction of flow of time. And the movie slows down close to merger. So this moment is when, for the first time, a common horizon was formed. And it very quickly settles down into a curved black hole state at the end, right? And you can see the gravitational wave peaks and troughs that are being emitted and traveling outward from the source. Okay, so this is a typical result from a numerical relativity simulation for binary black holes, and the waveform that came out of this particular simulation was the one that was used in the GW discovery paper in the figure shown at the left bottom here. So in the top two panels is the raw filtered data from the Hanford and Livingston observatories. And at the bottom is the closely matching equivalent waveform from numerical relativity. Okay. We are also able to perform simulations of neutron star black holes and binary black holes. And I'm, for just illustration, showing one of those simulations here. So what is happening here is that we have a black hole and a neutron star, which is going to be tidally disrupted by the black hole as time goes on. At this moment, we can see the star as tidally disrupted. It forms a small accretion disk around the black hole. And as time goes on, all of the material falls into the horizon. Okay, approximation without the necessary ones to perform numerical simulations. Okay, just give me 1 second. Okay. Hope you can still hear me. Sorry, I had a brief trouble with my
Yeah,
microphone. Okay. So how do we do these simulations? How do we perform these simulations? So that's what I want to talk about in the rest of the talk. And so let's start. So what we are doing is actually we're solving the equations of gravity. We're solving Einstein's equations, which, unlike in Newtonian gravity, which can be stated in this form, in Einsteinian gravity, the space-time itself is poised to be curved. And this curvature is represented by the metric of the space-time fabric. This metric is a tensorial field that is typically represented as a GAB tensor. Uh, um, and this field itself is determined by solving Einstein's equations, which is a set of 10 coupled second-order partial differential equations, subject to some initial and boundary conditions. So this is a highly non-trivial set of PDs, and solving them becomes difficult in dynamical situations, and we'll see how and why in time. So the very first attempts to actually solve these equations were made as early as 1964 by Hahn and Lindquist at IBM. And they were able to actually evolve Einstein's equations for a very short period of time before the simulations crashed due to numerical blowups. And we'll see why that happened. In fact, the problem that infested their simulations remained an open problem for the next 3 or 4 decades. Okay? Until about 2005, when Franz Pretorius was able to perform the very first stable binary black hole evolutions. So here is the paper that he wrote that year. And the two figures here show the trajectories of two black holes and the associated gravitational wave emission from that system. Soon thereafter, different groups around the world were able to also simulate these binary black hole systems. Uh, so there'll be the RIT group, Georgia Tech, Maryland group, and others as well. So briefly speaking, solving Einstein's equations is the very first step is to break down the manifest covariance and break the basically the concept of space-time into space and time explicitly. And that is because we are only capable of supplying initial data at one instant of time. So when we perform this 3+1 split, we find that the evolution equations, the Einstein's equations, they separate out into a set of two partial differential equations. The first is a set of evolution equations that tell you how the metric of the spatial slice evolves from one time step to the next time step, and how its extrinsic curvature, which is a measure of how the slice is curved when embedded in the larger space-time, also evolves from one time steps to another. And then another set of equations that we get are the constraint equations, which are basically constraining the behavior of the curvature within a slice itself. So these are elliptic PDEs that must be respected or solved at every time step, while the evolution equations tell us how to proceed further in time, given some initial conditions of your system. Right? So it's not unlike Maxwell's equations, for example, where you have evolution equations for the electric and magnetic field, but you also have some constraints that must be respected as time goes forward. So I have a question in the chat that I'm seeing. The question is, are these simulations performed using publicly available code? The simulations I described and showed, they were performed using the spectral Einstein code that I'll just talk about, and that is not publicly available. However, we are developing a new code base called Spectre, which is indeed publicly available. So I'll talk about that as well. Okay. So what makes this process challenging? There are many reasons what makes this challenging. The first of them is that we have many length scales in the system. We have the size of the black hole. Then we have the separation between the black hole, which is approximately a factor of 10 larger than the size of these horizons. Then the gravitational wavelength, the gravitational waves that we want to actually record may have wavelengths 2 orders of magnitude larger than the size of the horizons. So if we want to simulate them in a box, then that box has to be at least several of these wavelengths large in order to reliably extract these gravitational waves. So this puts a 3 to 4 order of magnitude separation between the smallest and the largest length scales that one must resolve at all times, right? Now, we don't know what coordinates to use. For a space-time, we don't know yet. If a priori, before performing a simulation, we don't know what coordinates would be better than others, which coordinates may or may not develop some singularity, some coordinate pathology or not, right? Now, the next would be, of course, putting black holes or singularities on a grid is always fun, right? Because computers really don't like infinity. So there are a few strategies which can help mitigate this. Now, the next problem, which number 4, is that Einstein constraints grew exponentially. And this is actually the key problem that remained unsolved for decades before Pretorius's simulations came out. So what was happening was that given some initial data, people were evolving the evolution equations. And soon, in a very short time of this evolution, the constraint equations became violated. And these violations, they grew exponentially with time, right? And that led to blowing up of the numerical solution, right? So you may ask, why don't we simply solve the constraint equations at every time slice? I think there's a question like that in the chat. And that is because this forms a set of tightly coupled elliptic PDEs that are very expensive to solve. So if we do solve them on every time slice, we will simply make the cost of these simulations intractable. We will probably be able to do one or two simulations in a year or so. Right? So that's why. Next thing is resolving shocks and discontinuities in curved spacetime is a non-trivial challenge. And then we have the computational challenges, of course. So we are at any time evolving PDEs in 20 to 40 variables. And if we evolve time globally, then that global time step will be determined by the smallest length scale in your system. So that is not an efficient thing to do, especially because the accuracy that is required by the LIGO detector is quite high. We require the simulations to be faithful to much less than 1 radian error in tens of orbits long simulations. Okay. But one powerful technique that we particularly used are spectral methods, and they work quite nicely in vacuum when we have purely black hole systems. So this brings it to our particular group's efforts, which are in the form of a code called spectral Einstein code, which is designed to solve Einstein's equations. And it has been in development since for the last 20 years or so, with more than 500,000 lines of C++, Perl, Python, and so on. And there are many institutions that are now part of this, but originally spec was written by developers at Caltech and Cornell. And ICTS is now very much a part of the group. So, yeah. Okay, so why do we like spectral discretization? Because the way we use spectral discretization is that any unknown field that you want to evolve, say u as a function of x and time, we decompose it in a choice of basis, such that the coefficients of our decomposition are really the true functions of time, while the basis functions are not. So they are only functions of space. This clearly brings a neat separation between the time and spatial coordinates. And this also means that all spatial derivatives that we want to calculate, the spatial derivative operator passes through these time-dependent coefficients and only acts upon the basis functions themselves, right? So which means that we can compute the derivatives exactly, as opposed to finite difference schemes, where the field is represented by the actual value of the field at different points in space. And in order to compute spatial derivatives, we must construct local interpolants and differentiate the local interpolant. And therefore, the accuracy of that interpolant is restricted by how many points are we actually locally taking to construct it. If we want a higher and higher order derivative, the more and more points we must include in this interpolation. And that will increase the communication cost between points. Okay. Whereas for spectral representation, the solution is actually represented in these as the sum of these basis elements. Okay. The next part of how spec has become a robust code is choosing a carefully designed domain decomposition around the system that we are trying to solve. So this is what the domain looks like for the binary black hole problem. Around each singularity, we place a set of nested spherical shells that are shown here in the top left figure. Then between the two black holes, we place grids in this particular form. And then further out, we have a domain structure that is tailored to the near field solution. And far away from the source, we typically simply have concentric shells because not much is actually happening here beyond the propagation of gravitational waves outside.
There is a question at the chat uh, box.
Uh, okay. Yeah. So the difference between finite difference and spectral approaches is, I think, visually summarized in these two figures, if you see carefully. In the spectral approach, your true solution, which is the red curve here, is represented as a sum of a linear combination of these basis functions with the assumption that the solution is smooth, right? So because we are making this approximation, we can make such an expansion. And now, if we want to calculate derivatives, we can calculate derivatives simply by knowing the derivatives of our basis functions. So if our basis functions are Chebyshev polynomials, we know their derivatives. If the bases are Fourier series, we know its derivatives and so on and so forth. Right? Now, in finite difference schemes, the field value itself is stored at every grid point as such. So calculating derivatives becomes expensive and error prone, which means that spectral methods for a fixed number of points, spectral methods are more accurate than finite difference methods in solving partial differential equations. Okay, we can talk about this in more detail. I'm gonna skip over that and talk about the evolution equations. Okay, so I've talked about how we split space-time into 3+1. Now, given some initial data at some initial conditions of the initial state of the system, uh, we want to perform an evolution of Einstein's equations. And we do that in a first order form. So we take the second order Einstein's equation, the evolution part of Einstein's equations, we reduce them down to a set of first order hyperbolic partial differential equations. And that's the form we actually use for our numerical evolutions. So here I'm writing the general form of a first order set of hyperbolic PDEs. So we have the time derivative here, we have the spatial derivative terms here, the contracted by this matrix, and the source terms, all the non-derivative terms on the right-hand side over here. So for Einstein's equations, the evolved fields U alpha would be the metric G AB, its time derivative pi AB, and its spatial derivatives phi IAB. But in order to turn the second order equations into first order equations, I'm sure you're all comfortable with, we have to elevate its first derivatives into free variables. So that's what we have done. So instead of just G as the free variable, we now have G and pi and phi as three separate free variables. And so we get PDEs in all these three that are typically of this form that I've shown here. At least the principal parts of those PDEs, which mean all the derivative, all the terms that include the derivative operators, are shown here, right? And these equations are, of course, subject to constraints, such as the gauge constraint or the simple constraint that uh, these definitions of pi and phi must be satisfied throughout the evolution, right? Because note that once we start evolving, it's not guaranteed necessarily that phi IAB, the free field phi IAB, will actually track the spatial derivatives of this free field GAB at all times, right? So this becomes an extra constraint that we must impose in addition to these evolution equations, typically, right? So what really happens is that if we write down the evolution system for these constraints, they turn out to have a term proportional to the constraints on the right hand side. And this is the term that was responsible for the exponential blow off of constraint violations for more than 3 decades or so. And this is controlling this term is what took the longest. It was one of the most formidable challenges in numerical relativity in the past, right? So how did we do it? How did people do it? In order to understand that, it's a procedure called constraint damping. I'm going to illustrate that using the scalar waves in flat space-time. So this is the second order representation of the scalar wave equation without a source term. The first step would be to reduce this into a first order form. So in order to do that, I have to introduce two new variables. pi, and phi, which are respectively the time derivative of psi and the spatial derivatives of psi, right? And now the constraint I get is this, that my phi I, the free variable phi I, should track the spatial derivative of psi at all times, right? Now, if you write down the evolution equation for this particular constraint, you find that it on the right hand side, we have an identical zero. So it's not quite as bad as Einstein's equations where we had terms proportional to C themselves, but it will still do the trick because in case numerical violations of this constraint crop up in the scalar wave system, those violations will never ever leave your domain. They will just stay there. They will not decay away. Those errors will continue to roam around in your domain as per this evolution equations, right? So what we can do is modify the original evolution system such that by adding multiples of the constraint itself. Now remember, at the continuum level, the constraints are identically zero. So we are not changing the physical solutions of these equations, right? What we are doing is we are changing the solution space in a way that the physical solutions are becoming an attractor. Yes. So by simply adding this term on the right hand side of just the third equation here, now if we write down the evolution equations for Ci, we get an equation of this form, which of course has a solution where the constraint will exponentially decay on a time scale that is governed by this constant gamma 2. So now we have a knob gamma 2 that we can move around, and we can damp away any violations of our constraints. Okay, so the same exact qualitative procedure is done for Einstein's equation. It's a little bit more complicated to explain. It may take a bit more time, but you'll see a few different combinations of multiples of Einstein constraints have been added. So these are the original first order PDEs of the evolution equations of Einstein's equations in generalized harmonic age, right? Earlier, I had shown you only the principal parts. Now I'm showing you all the terms in the partial differential equations, right? And because of the addition of these crucial key terms, now the constraints, Einstein constraints, become proportional to these e to the power minus gamma naught and gamma 2t. And now just by controlling the values of these constants gamma naught and gamma 2, we are able to damp away constraint violations exponentially.
Sorry, there's
Okay,
one
so I
more.
see another question in the chat. In the 3+1 decomposition in this case, does the boundary condition taken at t equals to 0 to infinity or minus infinity to infinity? So at the outer boundary, typically our boundaries, I'm going to talk about, okay. So at the outer boundaries, we typically we have to impose boundary conditions, right? So we impose boundary conditions only on the outgoing characteristic modes of the evolution equations. And we require that these outgoing modes continue to propagate out. They're not reflected back. So we basically want to have evolution domain where the outer boundary is transparent. Modes that are traveling outward, they leave the domain and they never re-enter. They should not be reflected back from the boundary and so on. Okay. So how do we deal with the singularity? For the spectral Einstein code, we excise out the singularity. What does that mean? So we cleverly design a domain such that it extends inside the horizon, yes, but it doesn't extend all the way to the singularity. So if this dark blackish region is the world tube of the horizon, of one of the two horizons, then we extend our domain up until this red cylinder over here, right? Which is right inside the horizon, but well outside the singularity that lies inside over here. So this also means that at this particular boundary, we don't need to provide any boundary conditions because there are no incoming or out. I mean, all the fields are mostly flowing out here, right? Nothing can come back in. Okay. Another key aspect of what makes spectral Einstein code robust is being able to adaptively refine the grid or the mesh depending on the needs of the PDE solver, right? So, for example, one way of measuring error is by measuring how fast our spectral expansion coefficients are falling off. Typically, in a well-behaved, smooth solution, the coefficients they can fall off exponentially. And at some point, we will truncate. We will choose to say, okay, we are only going to keep the 6 leading order terms, and that's it. Which means that the error we will accrue would be proportional to the highest order or the smallest coefficient over here. And this error is called truncation error. So we typically monitor the truncation error in all fields that we are evolving. So what do I mean by all fields? So we remember we are evolving the tensor G, the metric tensor, its time derivative pi, and the spatial derivative is phi. So gxx, gxy, gxz, say pi xx, pi xy, pi xz, phi x, tt, xxx, xyy, all of these components of all of these tensors individually are monitored at all times for their truncation errors. And the moment we find that truncation error has become unacceptably large, we refine the meshes in order to resolve that particular component of that particular tensor better. So typically what we find is that the AMR system, it places down a lot more grid points near the black holes. So in this schematic figure here, the two horizons are given here and here, right? This is the larger horizon, and this at the peak here is the smallest horizon. The height is the resolution, okay? So the resolution is lowest away from these two black holes, and it's more close to the bigger black hole compared to out away, and it's even more near the smallest black hole. And that's because the smallest black hole will have even the smallest length scales corresponding to the oscillations of its horizon that need to be resolved over here, right? So this figure illustrates what I was talking about qualitatively. So for example, this is an actual set of spectral coefficients taken from a real BBH simulation. And these are the top, I think, 15 coefficients or so as a function of time, right? And this black line over here at 4800 marks the moment of merger. This is where the two black holes merge, right? So you see that the error actually corresponds to the highest order coefficient here. So the error grows. And as soon as it grows by a certain amount, a new curve appears. And that new curve appears because we've just added one more basis function to resolve that field. The error grows again and we add more basis functions and so on and so forth. The same thing can be seen in this figure here. So blue is the target truncation error and the measured error oscillates like this, right? So this is one way of refining our meshes. Another way of refining would be redraw the whole domain also, which is also something that automatically happens. Okay. And at all times, we need to track the parent horizons very carefully because we need to place our accretion surfaces right inside these horizons. So any time we have errors in how well we are tracking the horizons, the accretion surface may intersect the horizon. And that means now we may have incoming fields at some part of these accretion surfaces, and that will destroy simply the solution. So this horizon tracking system is typically done in the following way. We represent the shape of the horizon in the form of an expansion in spherical harmonics. And the coefficients of this expansion, we control using a feedback loop control system. Okay. So going back to the original list of difficulties, these were the broad difficulties that I had discussed. With the spectral Einstein code, we have more or less managed to handle multiple length scales. We've managed to figure out what are good choice of coordinates, how to handle the singularities. in our system how to control Einstein constraint violations. And what still is not very satisfactorily resolved is how to handle shocks and discontinuities, and how to make these simulations scalable and less expensive, keeping the accuracy requirements in mind. Right. So these are the outstanding challenges of the field. Right. So we go back to the drawing board and we take up only the outstanding challenges, which are the multiple time/length scales, computational challenges, shocks, and high accuracy requirements. And we realize that people need to sort of think differently in terms of the whole paradigm of how these differential equations are being solved. So we decided that going forward, we need to make three new paradigm choices. The first is entirely throw away the discretization scheme that we have been using, right? And we ideally want to use a discretization scheme that has high order accuracy while being local, while not requiring too much communication from its neighbors. Why? Because if you require too much communication from your neighbors, you increase the communication cost, and so your simulations are then sort of limited by how much communication bandwidth your computers have, and that will slow down your simulations significantly. The next paradigm that we adopt is an entirely new parallelization scheme that can actually scale, which the current scheme does not, and I'll describe it in a bit. And finally, and is instead of evolving time globally everywhere simultaneously, we can evolve time locally in different pockets of our domain and stitch them together as we go along. Right? So let me talk about each of these three together. And this is sort of the part where I'm describing what we are doing to solve to address the future challenges of the field. So now, these were the four requirements that we require from the discretization scheme that we want to use, right? So the first candidate we have are finite difference methods. So the domain, I've shown only a one-dimensional domain here. So the domain is a set of co-location points, and the solution is locally represented as a polynomial that interpolates through these grid points, right? So now, in order to calculate derivatives, you must calculate this polynomial and differentiate that. So the accuracy of the derivative depends on how many neighboring points you stack together, right? So which means that while at low order accuracy, not it is this discretization is local. If you require high order accuracy, suppose you require eighth order accurate spatial derivatives, then you no longer can call this a local scheme. It will require communication from a lot of neighbors, right? Finite difference methods are able to handle discontinuities quite well, but they're also able to handle inhomogeneous grids, but not as well as maybe a finite element methods. The next candidate would be spectral methods, which we have been using all this while for binary black hole problems. And in this, the domain is represented by these separate elements. And within each element, the solution is expanded as on a local choice of basis functions. So in each of these subdomains, I have shown the first two basis elements, the constant and the linear basis elements, right? So the true solution, that is the green curve over here, is represented by a combination of the constant and the linear element, right? Okay. So it is now a local scheme even if you require a high order accuracy, because even if you, no matter what order derivative you need within dk, you only need information within this element. You will not need information outside this element to calculate derivatives here, right? So it's local at high order accuracy, local at low order accuracies. It's able to handle inhomogeneous grids, but it simply cannot do discontinuities. It requires the solution to be strictly continuous at all the element boundaries, right? Which means this is perfect for smooth solutions, smooth fields, but it's not so great when your fields are naturally going to contain discontinuities. Now, this is not much of a concern for black hole simulations, but it's a large concern for any system which has, say, neutron stars in the picture. And if you remember the movie I had showed you earlier, the neutron star had gotten disrupted by the black hole that it was orbiting. And the process of disruption, for example, if we were using spectral methods there, would require would require re-expanding the solution at every time point and so on. I apologize if that last point was not very clear. We can discuss that in the after my talk more depth. Then another candidate would be finite volume methods, right? So finite volume methods are simple to understand. So the solution is typically represented by cell averages within each of these sub-elements, right? So this is the true solution. And the blue lines represent the actual represented discrete solution over here. Now, they can obviously handle discontinuities, yes, but when we want to calculate derivatives, in each element, there is simply not enough information. So it needs more information from its neighbors, and higher order derivatives will require a lot of neighbors to inform. And therefore, if this is highly non-local at high order accuracy requirements, right? So finally, we come to the magic ingredient, which is a discretization scheme called discontinuous Galerkin. So these methods are not not very old. They were developed in 1990s or so. And what happens in these is that just like spectral methods, the solution is expanded locally. In each domain, it's expanded in a local uh, basis. But with the key difference that between the elements, an exact continuity requirement does not exist. An approximate flux of information is what DG methods require. So yeah. So this key difference with spectral methods gets rid of the handicap the spectral method had, which about handling discontinuities. And DG methods are actually local at low order and high order accuracy. And if, for example, if you want a high order derivative, just turn up the order of your basis in your element, right? And they can handle discontinuities, and they can handle inhomogeneous grids that you might require for tracking your system. Okay, so no spectral methods, no finite differencing. We'll go with discontinuous Galerkin methods, right? Now, the next new paradigm that I described was using local time stepping. So now let's just look at this domain for a couple of seconds, right? The two black holes, or to the two neutron stars, or whatever we're solving for, are sitting right in the center over here. We are not even able to see them at this level. Most of the domain is empty. All that happens here is the propagation of gravitational waves or electromagnetic waves, whatever they might be, outside, right? So trying to perform evolutions with tiny time steps, and by tiny, I mean time steps that are dictated by the length scales of the oscillations of the small horizon in your system. If we perform such small time steps everywhere, that's a terrible waste of computing, right? So local time stepping can and has been achieved, and what really happens is, if I reduce this 3D domain into 1 plus 1D domain, so space is along x-axis and time is along y-axis here, right? So what happens is that near the smallest length scales, we'll take small time steps. And for example, we'll take the smallest time steps near the smallest black holes. We'll take slightly larger time steps near the bigger black hole, and much larger time steps out far away from the source where we don't need to take very small time steps. And all the information that we need at these intermediate stages, we are simply able to extrapolate from the past information, right? So in practice, at the moment, we are able to achieve approximately a ratio of 16:1 time steps. So we can take 16 times larger time steps here compared to here, right? Okay. And finally, the last paradigm that we will need going forward into the future is how can we parallelize our calculations better. So currently we use a domain-based parallelization. What does that mean? So we have obviously split our entire domain into smaller elements. Yes. Now we take each element, assign that element its own computer, and that core handles all of the calculations associated with that element, right? So the problem with this design is we are thinking like physicists, we are not thinking like computer scientists here. So it's an easy design to think and implement about and think about and implement. But what in practice ends up happening is that the core that is assigned the smallest, I mean, the space-time region around the smallest black hole, it is typically the slowest of all. And everybody else finishes its tasks much earlier and then waits simply for that slowest guy to complete its work. So typically this leads to a lot of wastage of computing because of this global synchronicity requirement, right? So the new parallelization scheme that we embark upon is called a task-based parallelization scheme. And this is not something new in the world, in the sense that in the industry it has been used in the past and it is currently being used at large scales. It's only in astrophysics that we have now recently started using it. And conceptually, what is happening is we have a computational domain here that is shown schematically. So we have some elements in shown in blue and the boundary between the elements shown in purple here, right? So instead of thinking in terms of these elements, we now take the calculation requirements for all of these elements, put those requirements in a global object space. And then depending on how and when every calculation needs to be performed, any core can get a part of any of the calculation required. So what does that mean? It means, for example, when this fourth guy has done calculating the right-hand side of Einstein's equations in, say, this spherical shell, it's when it is finished with that, it will go and help the core that is calculating the right-hand side closer to the smaller black hole. It will not simply sit idle, right? So this is called task-based parallelism. All the tasks or the computing tasks are put into a global queue. And from this queue, the tasks are popped and pushed to various cores as and when they become available. So really, no core is ever allowed to sit idle and so on. And this can be quite a game changer. So wheels I described are leading to this future generation code that we are currently writing, and it's in its advanced stages now. It's called Spectre, right? And here I'm showing some scaling test for Spectre. So typically when we run spec or any other numerical relativity code, if we throw more and more computers at it, the performance doesn't strictly always improve, right? In fact, after a few hundred to maybe several hundred cores have been put on a single problem, the performance pretty much plateaus. So this is the scaling that current codes approximately display. Whereas Spectre, because of task-based parallelism and everything else, is able to scale quite well, all the way up to 500,000 cores that we were able to use on the Blue Water supercomputer in the US. And it scales linearly, which is very good, which is exactly as we want. And this demonstrates especially the power of task-based parallelism that we use. And this makes Spectre future-proof because, as we are seeing, it's not that individual computers are becoming faster. We are simply getting a lot more of those cores on each chip, right? Okay, I am going to skip this part and summarize here. Okay. So in summary, currently we are developing a code called Spectre, which is a radically forward-looking computational astrophysics code. While it is currently being designed specifically for numerical relativity, it can be quite easily used to solve fluid dynamics and other problems. And it has been open source since a long time. It's available on GitHub. You can just go to github.com/sxs-collaboration/spectre. This is a snapshot of its webpage. And the three key new paradigms that it uses are DG discretization, discontinuous Galerkin discretization, local time stepping, and task-based parallelism. Okay. And the use of task-based parallelism will enable the successful use of future exascale computing that we are heading toward. Currently, Einstein's equations, GRMSD equations have been implemented. Domains are constructed. We are able to approximately do mesh refinement. The treatment of the boundaries is complete. People are working on having the control systems work properly. And this is where we are at. So this is where I'll stop and take further questions. Thank you so much.
So thanks, Prayush, for a wonderful talk. And now the floor is open for questions. So you can unmute yourself and ask any questions that you have.